So in the last lecture, we started reviewing some examples of CVD. So we'll continue that, and we were discussing the epitaxial growth of silicon. Yeah. So we briefly discussed the difference between amorphous silicon deposition, polycrystalline silicon, and monocrystalline silicon. Very critical parameter here is actually the temperature. Yeah. And we have briefly discussed why you need higher temperature for the growth of crystalline forms. Okay. So you can see this thing now. If you go back to our discussion on the kinetics of the process, you had this growth rate, right, versus 1 by temperature. Okay, and so from low temperature, the deposition rate increased with temperature. So that was the reaction limited, right, and then it went into a mass transport limited regime. Okay, so we are going to higher temperature. So you're talking about your epitaxial growth. Then it is very likely to happen in the mass transport controlled region. So that is why we had seen a certain atmospheric pressure reactors, right, where the designs were like you have a wafer placed on a susceptor which is slanted. Okay, so you have a constriction in the cross section area through which the gas flows reduces as the gas proceeds. Okay, so this would then maintain the what? Stagnant layer in the process. So that is basically related to this. So you find for epitaxial growth of silicon this kind of processes. Okay. So this we have already discussed. Okay. Now, a couple of other points that we would actually discuss. When we discuss about epitaxy of a crystalline material, of course that is grown on another crystalline material. So the interface should not have any amorphous material. For example, I should not have silicon dioxide at the interface. Okay. So, but we have seen that if you take silicon and just expose it to atmosphere, a thin native oxide will naturally grow on the surface. Okay. So it is very important that we remove this oxide from the surface. Otherwise, you are going to grow defective silicon, or if there is a continuous layer, you are going to grow most likely a polycrystalline layer on top, because you don't have a crystalline template to follow. Because if you have a thin silicon dioxide, that is amorphous. Okay, so where will these silicon atoms go and sit? Not at a, what is the lattice site in an amorphous silicon dioxide? Okay, so we can't have it. So you need some process to remove the native oxide. So usually, you know, if you do this epitaxial growth, you need to clean the wafer, do HF dip. Immediately you load into the reactor where you do the process, okay, where you do the deposition. But there are, of course, that is then repeatability of this process and so on is important. So now there's one technique that you can use for removing the oxide in situ, okay, prior to deposition inside the epitaxial reactor. Okay, so you have this very simple reaction happening at these high temperatures. So if you have silicon dioxide on the surface, you pass hydrogen. Okay, so hydrogen will react with silicon. Of course, this is a reversible reaction, right? You may also have H2O oxidizing silicon. So you have the hydrogen etching the silicon dioxide will form water, and this needs temperatures above 900 degrees centigrade. And the silicon dioxide is extremely thin, okay, and it's 100% hydrogen. So you trace amounts of this water vapor will come, and that is taken out by your gas stream, okay. So you can then get pristine silicon surface, okay. So then you do the apraxial reaction. So this is something I've already seen. So the other thing that people have seen is that if you now you are trying to grow silicon on silicon using silane, okay. So one method that people have found to increase the mobility of the deposited atoms on the surface, okay, is to actually add more hydrogen, okay. But if it is too much, then what happens is that you actually would then dissociate or react this hydrogen, excess hydrogen, with the surface silicon, and then you may actually get the silanes, yeah, and then it starts to etch. So you don't want that condition. So it has to be then adjusted so that you get sufficient surface mobility, but it is not actually removing the silicon, okay. So reducing the growth rate. So when you have this, it's a reversible reaction. So you are actually adding hydrogen. So this should pyrolyze to give you silicon, and which will actually then give you 2 molecules of hydrogen. But then you are adding hydrogen from outside. Yeah, so then it might drive it in the other direction. Okay, so that is the etch process, right? But what is seen is that if you have more hydrogen, presence of hydrogen improve the diffusivity of silicon on the silicon surface. Okay, so then it can help you to actually grow a good quality epitaxial layer. Okay, so this helps in 2 ways. One is that this reaction, the reverse, is emphasized by adding more hydrogen, so the effective deposition rate reduces. You are pyrolyzing silane to get silicon, and the byproduct is hydrogen. But now you are adding additional hydrogen so that the reaction is retarded, because there is an, you have this reversible reaction, right? When you add hydrogen, more hydrogen, then this rate also picks up. So the net rate of deposition of silicon comes down. Yeah, so because you are, the point here is that, so you are trying to grow a crystalline film, and we have seen one of the condition there is that the silicon atoms that are deposited should find sufficient time to go and occupy a lattice site. Yeah, if the deposition is very fast, right? So then that is not desirable. Yeah. So 2 things that you are doing. You are actually retarding the growth rate, but also this would increase the diffusivity of silicon on the surface. Okay. So these are 2 things. In fact, a very interesting question is that we are talking about a good quality silicon, and older times people basically took silicon vapor, grew the epitaxial film everywhere. Okay. But when you started developing silicon MOSFETs, there came a time where you wanted to grow an epitaxial layer in certain parts of your device. Okay. So what it means is that certain parts of the device, then I should be able to selectively grow only in those regions. Okay. So this is, how do you do this? Yeah, how do you do this? So this is a CMOS device. Okay. So you can see this is a N-channel MOSFET. This is a P-channel MOSFET. You have the source drain. This basically shows different types of doping and depletion regions and so on. So we will not pay much attention here. So there are a couple of examples where you want to raise up this source drain. Okay, I'll show you two examples. One is that it is seen if you have a silicon germanium in the source and drain region of P-channel MOSFET, you can actually enhance the mobility. Okay, not so for the N-channel MOSFET. So then the problem for epitaxy is restricted to this. I should be able to grow an epitaxial layer here, okay, and here, nowhere else. Yeah, but both these things are on the wafer. Okay, so the what things are there? So you have an this is polysilicon, and this is what? This is your isolation, right? Polysilicon, and this is your nitride. So this is an oxide, nitride, the source, drain. This is polysilicon, and you have here silicon, nitride, and polysilicon, and so on and so forth. So now I need to cover up this polysilicon because I don't want to grow anything. I need to cover up this device because I don't really want to grow anything here. Okay. So that is one example. So I'm going to then cover up all these things, etch the source drain, okay, and when I actually make the transistor with a gate, I'm going to use an oxide on top of polysilicon. So this is some technology, will not go into the details. So I have by some means from prior processing some oxide on top. Okay. So I'm going to mask this area, right? I would etch this, okay, and then I will grow silicon germanium. Okay. So that is one process. The other is if I'm going to make this device on SOI, so that is here it would be oxide, thick oxide, right? And I should actually elevate the source drain to reduce the series resistance. There are two examples. So I want to grow this epitaxial layers of silicon or silicon germanium in select parts of the whole wafer. Okay. But then I take this wafer and I put it into a furnace, okay, and then I'm using silane or some other stuff, right, chlorosilane, to deposit the epitaxial silicon layer. It would deposit, usually it will deposit everywhere, okay, but you tell me, where will it be growing epitaxially? Pardon? Will it grow epitaxially everywhere? Only on silicon. Okay? Because you need a crystalline template for an epitaxial growth. Yeah? So you need semiconductor with a crystalline thing. So here talking about, meaning of course it can be insulator also if it is really crystalline, but then the crystal structures should match, right? Lattice constants should match. That is not, so in this case it is simple. I would have an epitaxial growth on the silicon. What about the insulator? Meaning the rest of the regions on the spacer, for example, on the isolation region, what would happen? Will anything grow? Will anything grow? Yes or no? Okay, what will grow? Yes, the chemical reactions, it will get deposited. But then, what would that silicon be? Amorphous, polycrystalline, silicon, meaning monocrystalline? It cannot be monocrystalline, right? Because it's growing on an oxide. Can it be amorphous? Pardon? Yeah, but okay. So, but we want to grow in this region epitaxial silicon. So, you need to go to high temperature. Okay. So, let's say 900 degrees centigrade. But amorphous silicon, once you take amorphous silicon, you expose it to high temperature ambient like 900. Forget about 900, 700, 650 and onwards. It starts to crystallize, but it will actually form polycrystalline. Okay. So, you would form polycrystalline silicon here, monocrystalline here, polycrystalline here and so on. Okay. But then I have problem, the silicon is everywhere. So, I can't just, it's not a selective deposition. It's not, meaning crystalline silicon is selectively deposited, so you can claim that, but silicon is everywhere. Okay. So, how do we solve this problem? So, that is the selective epitaxy problem. Okay. Any way that you can think of, you forget about all these things. Yeah, you are depositing, but we had some clue from the previous slide. So, the deposition is a chemical process, right? Chemical reaction. Yeah. Is it possible to do something there? Pardon? Well, so he's, yeah, very good. So, he's saying that add something which will react with your silicon. Okay, good. Yes. What is he saying? Yeah, okay, so you are trying to etch silicon. Do you want to etch all the silicon that is deposited there? Only the polysilicon. Yeah, I want to deposit monocrystalline on monocrystalline silicon, but wherever polycrystalline is etched, I need, it will get deposited, but I will add something which will etch the polycrystalline silicon. So then, but do you think it will not etch monocrystalline silicon? So what is the difference between monocrystalline and polycrystalline silicon? Correct? There are grains, lot of defects. Okay, will that help? Etch rate will be different. If you have a monocrystalline and polycrystalline, the etch rates will be different. Okay, so you are depositing the mono and poly at the same rate, right? Okay, and then you are etching, but because the polycrystalline silicon is defective, it will be etched faster. Monocrystalline would also be etched, but much slower. Okay, so we need to now add an etchant. So that is what it is. So now again, what kind of etchant, based on whatever we have discussed, is possible? Pardon? Hydrogen is one possibility, yeah, but anything else? So when you form, you use hydrogen, that's a possibility. Maybe there are, so this is one possibility, but is there anything else? So you can use silane, but I also mentioned chlorosilane, right? Does that help you? Meaning, give you some hint? Anything else that I can use? Yeah, so you can use HCl, not the acid that is in our stomach. You know this, right? Yeah, there is a lot of HCl in our stomach. Okay, so it's not that acid because it's actually HCl gas dissolved in water. Okay, this is dry HCl. So you mix that. So this is what the description we had, right? So silicon or silicon germanium should grow epitaxially on top of crystalline silicon. and no silicon or silicon germanium should grow on top of oxide or nitride. So that is our requirement. Okay. So these are two examples. Yeah. So this is an example where you can see the your transistor.
In the last slide, why don't we mask the other regions and then do the?
Yeah. So the problem is, you look at this. This is my transistor. This is a gate. I want to mask this tiny thing there. A problem. Okay. These are very small dimensions. Okay. If I am doing a masking, then I already mentioned there is something called alignment. Yeah. So I will have to leave a lot of space to account for that error in alignment. Okay. So I will not do that. If possible, as much as possible, I would like to use what is called self-aligned process. Okay. When I want to make extremely small dimension features. So this is the SOI example I mentioned. You have this looks like your gate, okay, and this is your spacer, and then so this should be your source drain level, right? We have seen gate and then source drain, but it is elevated. So basically, this is an epitaxially grown silicon layer, okay, and this is embedded silicon germanium in the PMOS for strain enhancement. So that will give you a high hole mobility. So this is a cross section TM of this Intel processes CMOS process. So you can see this is for PMOS devices, right? This is the your gate, okay, spacer, right? And this is a channel region. They have etched the silicon like this, and then deposited silicon germanium by selective epitaxial process. Okay. So this is the level of your source drain usually, but now it's actually grown beyond that. Okay. Now how do we do this? So you can see it here. So silicon or silicon germanium would grow epitaxially on silicon, right? Polycrystalline silicon or silicon germanium would grow on the oxide and nitride. So this contains crystal grains, and grain boundaries contain plenty of defects. So the approach is to introduce a chemical etchant, okay, to the reaction which would etch silicon or silicon germanium as required. Okay, so that is what we are going to do. So you add HCl, then so polycrystalline material may be etched faster than crystalline material due to presence of defects. So if you add HCl to this gas flow, so that can etch. So this is again a reversible reaction. This is a volatile compound. It's a gas at the process temperature. So you can actually, this will be carried away. But so you can, this etch rate would be faster for polycrystalline silicon than monocrystalline silicon. Okay. So you are actually depositing and etching, right? And wherever polycrystalline is deposited, the etch rate is faster. So you can see that you can find the sweet spot in your process, okay, where there is effective or net deposition rate of epitaxial silicon, right, is positive, but the net deposition rate for polycrystalline silicon is negative or 0. Okay. So this is what it says. This is another example. So Sanchar Ajay is doing PhD with me. So he is actually doing this very interesting process. So you have a silicon wafer, silicon dioxide. You have this gold nanodots. So we have seen, in previous lectures, how do you form this metal nanocrystals during the initial nucleation phase, you stop the process, or you deposit a very thin layer and anneal it, heat it, so you actually break it into nano dots. So you can see these are the nano dots of gold, okay. And then he takes this and then exposes it to silane in a CVD reactor. So something very interesting happens. So this will actually grow like this, okay. So this would be your silicon, and then this is gold. Okay, you started with the gold on the silicon dioxide. Okay. So what happens in this case is that this will paralyze and the silicon dissolves in the gold. Okay. So you have this, the silicon gold mixture you will start to get. So it has a meaning the mixture would have a lower melting point, and then you can form a eutectic and so on, right? And then you will start to, so basically this mixture would actually melt at lower temperature than either melting point of gold and that of silicon also, right? So you have a liquid which contains gold and silicon, but it's already a liquid, okay. So that is why it is called vapor liquid solid growth. And then as silicon keep on dissolving in this liquid, it becomes supersaturated with silicon, okay. So silicon will then start to precipitate, okay. So you can see this silicon start to precipitate at the bottom. This liquid droplet is at the top. So then it will start to grow here, right? It grows up like this, okay. So then the dimensions of this, the diameter and so on, would be actually depending on the diameter of the gold nanodot. So depending on the process conditions, you can actually grow this. So this is low temperature, okay. So you can see this is a beautiful SEM image of this thing, nanowires that have grown by this technique. Okay. So you have, you can also, meaning they are changing directions as they grow. That's attributed to change in the pressure in our reactor. So if you you can also grow straight arrays of straight nanowires. Yeah. Then you need a very precise control on the pressure. Okay. So we don't have that. So this pressure fluctuates. You can see this. If you look at any of this, right? The tip looks somewhat different. Yeah. Look at the tip. Okay. The tip has a slightly different contrast. So that tells you something. So we will see what happens. This case. Okay. Okay. So if you take one of these nanowires and do a high resolution SEM imaging, you find this. Okay. This is a nanowire. Basically, you put it in water, this, and then shake it. So these nanowires will break. Okay, and you can take that water and then disperse it on some substrate. So and then evaporate the water. So you will actually get these nanowires here and there. And this is an image, and you can see here very long nanowire. So this is about 70 to 80 nanometers. And meaning, of course, the diameter is changing. Okay, and this is at the tip you have gold. Okay, and you can see this thing in. So this is a TEM image of the tip. So this is a silicon nanowire, and then gold. Okay, and you can you can verify this. So this is actually what is called a X-ray image here. So it gives you gold consolidation, okay, at the tip. The silicon, it is actually low. This is EDAX. Electron dispersive X-ray spectroscopy. Yeah, so he has actually then made devices using this nanowires. And some work is also going on to make sensors using this nanowires and so on. Okay. So what we will do now is to actually look at plasma enhanced CVD. So far we have looked at thermal CVD processes. We have looked at several examples, right, of materials that you deposit very commonly in VLSI. Okay, and we have focused on mostly silicon compounds, right? Silicon dioxide, silicon nitride, amorphous silicon, polycrystalline silicon, diffraction silicon, and so on. Okay. Now, plasma enhanced CVD is very interesting. In fact, if you remember, one of the first slides in this module, I had shown you a kind of analysis of a CMOS process till you complete the first level of metallization. Okay. So there you had, of course, thermal CVD processes, but most of the processes were actually plasma enhanced CVD. If you go back and see this. Okay. So it is very important, and there is a reason for that. Can you guess what could be the reason? Yes. Okay. Okay. So yeah, what she is saying is that once you make your source drain and make the contact, let's say you have nickel silicide there. Okay. So can I go for high temperature deposition of anything on top? Okay. So you can't do this. Yeah. So for example, if you look at nickel silicide, okay, nickel silicide makes good contact. So there are different phases of nickel silicide. Okay. So common things are Ni2Si, NiSi, okay, and NiSi2. Then there are many others, Ni3Si4 and all these things. Okay. Because this is a transition metal, so it has valency is not like, you know, something like sodium. So it's usually just valency of 1. Okay. So transition metals can make different types of compounds, yeah, with the same binary compounds with the same element. So for good contact resistance, you would really like to have monosilicide, nickel monosilicide. If you take titanium, you would like to have titanium disilicide, cobalt disilicide. Okay. The problem is that if you have NiSi and you heat it, it's sitting on silicon. It will react with the silicon, and then that will become NiSi2. Okay. So what is happening in that process? It's eating silicon. You can see this, right? But you have a junction that you have formed. So if it eats the silicon, it's going to go closer to your junction. Junction becomes leaky, your contact resistance goes bad, so overall not good for devices. Okay. So plasma enhanced CVD helps you in this scenario because you are not heating the substrate to high temperature. Yeah? You're creating a plasma, so you are actually counting on the excitation of all these reactants to break them, you know, you break the reactants into radicals, ions, and so on and so forth that we have seen, right? And they can be excited to higher energy by accelerating them in the plasma. And there are collision processes in the plasma that actually transfer energy to all these species. Okay, so I don't have to heat my substrate. Okay, so the low temperature, so you have some activation energy required for the thermal reaction to happen. And so far what we have seen is we are actually heating this thing, right? The substrate, but then now we are going to use plasma. Okay, so I'll excite this reactants to higher energies, and then they can react. So substrate temperature can be significantly low. So you can read this. So these are some examples for if you take the silicon nitride deposition. Okay, so we had seen on a previous slide. I showed an example of silicon nitride deposition, 780 degree centigrade. Okay, so thermal CVD requires something in that range. But I can deposit silicon nitride on silicon wafer at room temperature if I am doing this process in a plasma. Okay, but don't ask me what would be the quality of this. They will actually have different qualities. Okay, and it will not be Si3N4. It will be some other stoichiometry, and it may have other stuff from what you use for deposition. You are going to deposit with silane and ammonia, for example. So they can have silicon and nitrogen are in silicon nitride, but also the reactants contain hydrogen. So you may have some hydrogen incorporated, density of the film, and so on and so forth. So you are going to compromise something, but the fact is you can actually deposit at lower temperature. Okay, so compatible with all the metal layers that are below this film. So that is the important thing here. So a lot of these things what we have seen, what we are going to see here are actually common to all plasma systems. What happens there is a lot of things are very common. Okay, so what we will just do is we may just recollect some of them and review in the context of CVD deposition. Okay, so you have ions in the plasma may be used for sputtering, leading to a combination of deposition and physical etch possibility. You are doing a CVD deposition, right? Chemical vapor deposition, but in the plasma I also have ions. I can use them for sputtering. So I have a combination of deposition and etch. Okay, so that is possible. Yeah. So there are certain applications where this is used. I can make a dense film at low temperature by using some heavy ions to bombard the surface as they are actually getting deposited. You have seen this, the way that they make the road, right? Put something, tuck, tuck, tuck. Yeah, something like this. Yeah. So you are going to deposit your stuff, but then you are using argon ions to do the road there. Yeah? Make it a solid, dense stuff. Okay. You can use this for cleaning the wafer before deposition and things like this. Okay. Used for cleaning the chamber also for after deposition. So this is all possible. Now the other thing is that you have seen variety of species not available in a thermal reactor may be present. So an example is again silicon nitride deposition. If you are using a thermal CVD, you will actually have silane, one typical example, or some chlorosilane, okay, and ammonia. Okay, I can't have just silane and nitrogen because that nitrogen will not react at that temperature. But if I am using PCVD, the plasma will crack this. Okay, yeah, N2 will become N2N, but then this N atom is very reactive. So that can then start to react. So this means that larger variety of reaction pathways and things that you cannot use at in thermal CVD may already create this thing. But that also is a problem. I have mentioned this, that you can't use nitrogen as a diluent gas. I can't use nitrogen to dilute anything in a PCVD reactor unless I am ready to accept it as one of the things that may get into my film. Okay. So this is exactly the same. Okay. The construction may change because here you're going to use, unlike in a sputtering system, where you're going to use a sputter gas, right, which is usually an inert gas like argon, okay, and typically you deposit oxides, nitrites, and so on. So you may have oxygen, nitrogen, but not toxic gases, okay, usually not very dangerous gases, okay. But when I'm doing PECVD, I may actually pass silane, phosphine, and so on and so forth. So this whole thing will have to now handle corrosive and pyrophoric and toxic gases, okay, very important. So if I'm actually going to use some chlorosilane, so chlorine will be produced in the reaction, and that may actually react with the metal used for constructing the reactor chamber, okay, corrosion, okay. So I need to, meaning, so as a schematic it looks the same, okay, but in the construction the details will differ because of the kind of stuff that we will use.
So what exactly is the plasma doing? What exactly is the plasma doing?
We have seen this, right? This is what the plasma does.
In this chemical reaction.
So we'll come to that. We'll come to that. So this is what we'll see that in a moment. Okay. So we are just reviewing what we have already discussed, right? And in the sputtering process, we only took advantage of the ions, heavy ions, which can be accelerated through the dark space. Okay. But here we will look at other possibilities. Yeah. Here and also in etching, we will look at other possibilities. So this is something we have already seen. So energy is transferred to the plasma by capacitive coupling. So this is actually the parallel plate capacitor arrangement we have seen on the previous slide, right? And then, so this is, we have seen deposition, chemical etch, and sputtering can be achieved by using the ions and also free radicals. So we'll just see that on the next slide. Okay. So what all things are produced in your plasma? Okay. So because you have the electrons hitting the molecules, right? This is how you actually ignite the plasma, right? So there are some electrons even in this gas. It's not completely, meaning if I take the whole thing, it is neutral. So there will be a little bit of ionized atoms, molecules, and electrons, very small amounts. But then you are taking advantage of it in to create a plasma. You are actually accelerating the electrons, and then they will start to break down. Yeah, if you accelerate them to fairly high energies, they can then cause ionization of the molecules, right? All these things can happen. So you have this electron is actually excited electron. It's already accelerated. Okay. So it then interacts with a molecule. So this is a diatomic molecule. And then many things can happen. One of them is that it just transfers the energy to this molecule, does not break it. So the molecule has higher energy. It's not at an ion, it's not split up. The other possibility is that the energy is sufficient to actually break it into two atoms. Okay. The other possibility is that you can actually knock off an electron from this. It depends on what this X is, right? And you can have a dissociative ionization. So you get one ion but also one atom which is excited. So these are all excited atoms. So these are not, meaning atoms by themselves are most of this case like oxygen, O2, right? You split into two oxygen atoms. The oxygen atoms will be much more reactive. Okay? With two oxygen, they are very happy, right? Yeah? Unless there is something very attractive, they don't break up. Okay? But if you break them up, then the situation changes, right? Dissociative ionization is something that you have, so you get an ion plus an atom. Okay? All these things can happen. So we looked at for the previous case, sputtering this thing. Looked at this, and you are now going to accelerate those ions. So in sputtering, you are using argon ions typically, right? That would not anyway not react with anything. Okay. So you are using argon to basically bombard the surface. But in a CVD process, you may not use argon. You are going to use nitrogen, for example. You want to use silane. Okay. So then the situation changes. This actually would be, or I am going to use an oxygen plasma. Okay. Then I will have free radicals, oxygen atoms with high energy, oxygen ions, and so on. So free radicals, ions and electrons, so I can use the free radicals for chemical reactions. So this is very important. Free radicals can be used for chemical reactions. So we use the ions for sputtering. And in deposition, you're going to use the free radicals. Okay. Depending on what the free radical is, what element it is, right, or what species it is, it can cause deposition or it can also be used for etching. Essentially, it is a chemical reaction. So if the chemical reaction result in a solid material, that can get deposited on the vapor. But suppose that result in a volatile compound at the process temperature, if it is volatile, then that goes out, because you are actually, the whole system is under certain low pressure, right? Yeah? Lower than atmospheric pressure. So you are pumping it out. Okay. So depending on whether you form, the chemical reaction leads to a solid material at that temperature or a volatile compound, okay, you can get a deposition or an etching. Okay. And then you have additional thing that you have ions, you can actually accelerate them, that can also lead to sputtering. That's a physical etching. Okay. So you have three possibilities. One is a chemical reaction, CVD, deposition, and then there is a chemical reaction leading to etching, and then a sputtering process. In a CVD process, we had only two options. Ions were not present there. Thermal CVD. You could have deposition and etching. Okay. So here you have one more thing to play with. Pardon? That will not form any stable compound. Yes. So you let in silane, for example, or oxygen. Right? You are actually creating plasma of that. Okay. So the same discussion as before. Only thing is that this has to be seen in the context of deposition. The sputtering, we are discussing this in the context of etching. You are using ions for etching, right? But here we are talking about the deposition. So all these things will actually, you can see the thing, transport of the ionized species and radicals through the plasma. Reactions in the plasma is not very desirable in this case, because if you want to deposit, let's say, silicon nitride, okay, and silicon nitride forms in the plasma of silicon oxide, so then they will start to agglomerate in the plasma itself, and then drops of this will actually be deposited. So you may, if you don't have the right conditions, you deposit, on a silicon wafer, silicon dioxide, it will look like a powder. And just put a finger on top of it, just comes off. Okay, this is not a film. Okay, so the gas phase reactions, you have to be careful that you don't get this. Okay, very important. There are a lot of other things that can lead to this particle formation and deposition on the vapors. For example, if you want to deposit silicon nitride and so on, right? Silane and ammonia, for example, right? but there is some tiny leak somewhere, and then air gets into this chamber. What happens? So that contains oxygen. So you will have silane would spontaneously burn in oxygen. Okay, so I have a problem. Well, a powder of silicon dioxide will be formed, and then that will fall on a vapor. Okay, so a lot of things in practice you need to take care of a lot of things here. You can use these ions radicals for depositions and electron sputtering. Gas can be added, for example, if I want argon, xenon, and so on. So this leads to modification of the deposited film, and we will see some examples. Okay, and this is, we have seen, depending on the energy of the impinging fast particles, a lot of things can happen. Okay, so you again take advantage of this in the process as you wish. So this is, we have seen it previously, right? The sputtering of the growing film that can be utilized. So I'll show you some examples. Displacement, cascades, and so on. So this is also enhanced adhesion due to fast particles because of intermixing, cleaning of the surface, and things like that. Okay, so now some reactor configurations. So this is what we were discussing. You have this two electrodes, right? And this is a capacitively coupled plasma system. This is an inductively coupled plasma system. So we have this and also this inductively coupled plasma system. So you have a chamber, and this actually tube goes up, right? And there are these RF coils wound around it. Okay, so you apply an RF power here, that will create a plasma. Okay, we can get a plasma torch onto this, and that gives you the position on this. And since you are applying an RF power using an inductor, it's possible to confine the electrons within the space, and you can get higher density of the plasma. So it's also sometimes called high density plasma systems. Okay, and sometimes also called remote plasma, because the plasma is created away from the substrate. Okay? The excitation is given here, but in this case, the substrate is part of this process. Yeah? You are applying a voltage to create the plasma to the substrate terminal, right? And you can, if you go to YouTube and look for microwave plasma, and you can also do this experiment at home. Just be a little bit careful. Everybody would have microwaves at home, right? You can do this experiment. You can see these videos on YouTube with a disclaimer, be careful while doing it. If something happens, I am not responsible for that. Okay? So, but you can do that kind of stuff. Okay? So, this is a microwave plasma. There are also commercial systems available. And you can see a plasma glow actually in this microwave systems. Actually, people, in the lab, many labs, they build small plasma etchers and so on using microwave ovens discarded from homes, for example. Yeah, so this is possible. So small systems can be always made. Okay, so this is this photo I had shown you previously also. This is actually looking into a plasma chamber through there is a window, okay, a glass window, quartz window, to which you can actually look at. Meaning you don't look at it. You use use some protective UV protective goggles should be used. But you can take photograph, and the color depends on what species is there, what gas is used in this case. Okay, we talked about optical emission spectroscopy and so on, right? And this is actually a generic technique. People use it for analyzing. There's something called ICP-AES. Yeah, there's an instrument in SAIF CRNTS, which is inductively coupled plasma, and then you are actually analyzing the emission, okay, optical emission. So these are some of the applications of PECVD. Low temperature of deposition, silicon nitride amorphous silicon deposited by PECVD may contain more hydrogen than LPCVD films. I'll show you some data on this. So when you deposit this, you're going to do the deposition at low temperature, let's say, yeah, using PECVD. So you may get some hydrogen in the film. Okay, this is not necessarily bad, yeah, because, for example, you might have heard about this thin film transistors used in displays. Displays, they use thin film transistors. Okay, and that's not you don't use crystalline silicon for making it. This is huge, right? Displays are very big. Okay, so you can't have that big a crystal, right? Wafer. So how do you make this? You have a glass, and that is something is deposited on it. So this is a thin film, and you use that as channel material in your transistor. Okay. A display has to be refreshed at what rate? Maybe 30 frames per second. So it doesn't have to be very fast. So you use inferior quality semiconductors which don't have very high mobility. So one of the candidates is amorphous silicon. Okay, so somebody was asking this question. Amorphous silicon is very defective. Okay? Bonds are broken, there is no crystalline structure and so on. So you need, then I can't make any electronic device with this. So I need to passivate the defects. Okay, so you need hydrogen. So typically this thin film transistors or thin film solar cells made using amorphous silicon would have about 10% hydrogen in it. So it will be hydrogenated amorphous silicon. Okay, so that can be grown. Silicon nitride with hydrogen is used as a passivating layer in silicon solar cells. So the hydrogen during a high temperature process subsequent to the deposition diffuses into a crystal, okay, passivate defects inside the crystalline silicon. Okay, so a lot of things can be done. So it's not necessarily bad that we get some stuff from the precursors in the deposited layer. Now this is another application, stress control. So this is used for enhancing mobility, and the stress can be actually controlled by controlling the amount of hydrogen in the film. Low thermal budget, that I already mentioned previously, right? I think we'll stop here. Yeah. So you can now do other things. For example, possibility to combine reactive ion etching and deposition. Okay. So this is used for gap filling. So we'll show that. See that later. Okay. Or sputtering can be used for etching. Okay. Good.